while the great filaments of the cosmic web stretch across the voids, weaving the skeleton of the universe on scales that defy human imagination. There is a more intimate, ghostly drift happening right here, within the immediate vicinity of our own planet. We must now shift our gaze from the telescopic to the microscopic, from the light years of intergalactic space to the femtometers of the subatomic realm. For the story of dark matter is not just written in the architecture of galaxy clusters, but in the silent, incessant flow of particles that passes through the Earth every single moment as our solar system orbits the center of the Milky Way, traveling at a speed of 220 kilometers per second. We are not moving through empty space. We are plowing through the dark matter halo that envelops our galaxy. This creates a dark matter wind, a constant breeze of invisible particles that washes over us, passing through the atmosphere, through the bedrock of our continents, through the concrete of our cities, and through our own bodies, leaving no trace, no ripple, no sensation. To these particles, the solid matter of our world is as tenuous as a mist. The electromagnetic forces that bind our atoms together, giving walls their solidity and the ground its firmness, are invisible to them. They feel only gravity, and perhaps the weak nuclear force, meaning they glide through the electrical fields of our atoms like a phantom walking through a wall. This local drift is the subject of one of the most intense and quietest scientific endeavors in human history, the direct search for dark matter. Because we cannot see it in the sky with conventional telescopes, we have decided to build traps, waiting for the 1 in a trillion moment when a dark matter particle might accidentally collide with an atom of ordinary matter. To hear this faint whisper, we must escape the noise of the surface world. We must go deep underground, burying our ears beneath kilometers of rock to shield our delicate instruments from the cosmic rays that constantly rain down from the sky. In the deep mines of South Dakota, in the tunnels beneath the Grand Sasso Mountains in Italy, and in the nickel mines of Sudbury, Canada, physicists have constructed cathedrals of silence. Here, in the cool, dark caverns, reside the detectors, great tanks filled with noble liquids like xenon or argon, chilled to temperatures that would freeze the air instantly. Consider the xenon experiment or the LUX Zeppelin detector. These are vessels filled with tons of liquid xenon, a dense, transparent fluid. The principle is one of agonizing patience. The scientists wait for a particle from the dark matter wind, a weakly interacting massive particle, or WIMP, to strike a xenon nucleus. If such a collision occurs, the nucleus will recoil, releasing a tiny flash of light, a scintillation, and liberating a handful of electrons. Photomultiplier tubes lining the tank, sensitive enough to detect a single photon, watch the darkness of the liquid, waiting for that specific telltale signature. The rock above blocks the noisy cosmic rays. The purity of the materials blocks the radiation from the detector itself. It is a vigil kept in the dark, a hunt for a ghost in a sealed room. For decades, these detectors have run, staring into the liquid, pushing the limits of sensitivity further and further down. They have heard the background chatter of neutrinos, the subtle decay of impurities, but the dark matter particle remains elusive. The silence of these detectors is profound. It tells us that dark matter interacts even less frequently than we had hoped, that it is even more ghostly, even more detached from our luminous world than the simplest theories predicted. This silence has forced us to reconsider the nature of the drift. For a long time, the leading theory was supersymmetry, a beautiful extension of the standard model of particle physics, which posits that every known particle has a heavier, invisible partner. The WIMP was the natural candidate emerging from this mathematics, a particle with the mass of a heavy atomic nucleus that was produced in the thermal bath of the Big Bang. But as the Large Hadron Collider smashes protons together at energies that recreate the conditions of the early universe, and as the underground detectors remain quiet, the WIMP hypothesis is under siege. We are beginning to wonder if we are looking for the wrong kind of ghost. Perhaps dark matter is not a heavy particle, but something incredibly light, something that behaves more like a wave than a point-like object. Enter the Axion, a hypothetical particle originally proposed to solve a completely different problem in quantum chromodynamics related to the symmetry of the neutron. Actions would be billions of times lighter than an electron, so light that their quantum wavelengths would overlap, causing them to behave like a vast, coherent field, a Bose-Einstein condensate on a galactic scale. If the dark matter halo is made of actions, the drift is not a rain of bullets, but the oscillation of a wave. To catch an action, you do not use a tank of liquid xenon. You use a resonant cavity, a metal box placed in a strong magnetic field. The theory suggests that in the presence of a magnetic field, an action can occasionally convert into a photon, a particle of light. Experiments like the Axion Dark Matter E-experiment, or ADMX, are essentially radio receivers, tuning a dial through the frequencies of the cosmos, listening for the faint hum that would signal the conversion of dark matter into radio waves. It is a search for a cosmic radio station that has been broadcasting since the dawn of time, a station we are only just learning how to tune into. While the particle physicists hunt in the deep earth, the astrophysicists look back to the sky, finding that the cold dark matter model, despite its success in explaining the large-scale web, faces challenges when we zoom in to the scale of individual galaxies. This is where the drift becomes turbulent, in the simulations where dark matter is perfectly cold and interacts only via gravity. The centers of galaxies should be incredibly dense with dark matter, forming a sharp peak or cusp. However, when we observe real dwarf galaxies, measuring the rotation of their stars to infer the density profile, we often see a core, a central region where the dark matter density is flat, constant, rather than peaking sharply. This discrepancy is known as the core cusp problem. It is a subtle mismatch, a hint that perhaps dark matter is not perfectly cold, or that the physics of the ordinary matter, the exploding stars, the winds from black holes, is churning the dark matter, heating it up and pushing it out from the center. Furthermore, the simulations predict thousands of tiny satellite galaxies swarming around a giant like the Milky Way, a buzzing hive of subhalos. Yet for a long time, we saw only a dozen or so bright satellites, the Magellanic Clouds, Draco, Ursa Minor. This missing satellites problem troubled astronomers for years. Where were the thousands of other subhalos? Were they there, but dark, devoid of stars? Or did they never form? In recent years, deep surveys like the Dark Energy Survey have begun to find faint, ultra-diffuse ghost galaxies, wisps of stars barely brighter than the background sky, suggesting that many of the missing satellites are there, just incredibly hard to see. But the numbers still don't quite match the pure, cold, dark matter predictions. This has led to the proposal of warm dark matter, particles that move faster than WIMPs, blurring out the smallest clumps, preventing the tiniest subhalos from forming, or perhaps self-interacting dark matter, where the dark particles can bounce off one another, creating a pressure that smooths out the dense cusps at the centers of galaxies. This interplay between the smooth, large-scale drift and the messy, small-scale physics creates a picture of a universe that is both simpler and more complex than we imagined. The dark matter is not just a rigid scaffolding. It is a fluid that responds to its environment. It drifts, it clumps, it may even collide with itself. The drift is a dynamic process. Imagine the dark matter halo of the Milky Way not as a static sphere, but as a living ocean with tides and currents. When a smaller galaxy falls into the Milky Way, its dark matter halo is stripped away by tidal forces, creating long streams of dark matter that wrap around our galaxy like ribbons. We are currently detecting streams of stars, like the Sagittarius stream, that are the debris of these cannibalized galaxies. These stellar streams are riding on invisible rivers of dark matter. By mapping the motion of the stars in these streams, we can trace the shape of the dark matter river underneath. If the dark matter halo is lumpy, the streams should be disturbed, showing gaps and kinks where a subhalo of pure dark matter passed through. We are looking for these gaps now, hunting for the dark impactors, invisible clumps that possess no stars, but have enough gravity to punch a hole in a stream of stars. There is a profound beauty in this slow, invisible violence. The universe is a place of constant consumption and growth. Dark matter drives the mergers. It brings galaxies together, its friction slowing them down so they can coalesce. Without the drift of dark matter, galaxies would fly past one another in the expanding universe, lonely ships in the night. Dark matter is the friction, the glue, the gravity that allows complexity to emerge. It allowed the gas to pool, the stars to ignite, and the heavy elements to be forged. In a very real sense, we are the children of the dark drift. Our carbon, our oxygen, our iron, all forged in stars that formed only because dark matter created the gravitational wells to hold the gas. We are the visible foam on the dark ocean as we stare into the liquid xenon, waiting for a spark, or peer into the voids of space, mapping the distortions of light. We are engaging in a conversation with the invisible. We are asking the universe to reveal its hidden face. The fact that 85% of the matter in the cosmos is unknown to us is not a failure of science. It is the fuel of our curiosity. It tells us that there are forces and particles waiting to be discovered that could rewrite the laws of physics. The drift of dark matter through the cosmic web is the drift of a mystery that spans the entire history of time. From the first moments of the Big Bang to the final fading of the last star, it connects the largest scales of the filaments to the smallest scales of the particle detectors. It is a single, continuous story of gravity's silent, patient work. Let us return to the image of the web. The nodes, the clusters, are the cities of the universe, blazing with X-ray light, filled with thousands of galaxies. The filaments are the highways, the dark roads along which matter flows. And the voids are the wilderness, the empty deserts. But even the voids are not truly empty. They are expanding, pushing the filaments apart. This brings us to the final, and perhaps most unsettling, player in our story: dark energy. While dark matter pulls, dark energy pushes. While dark matter builds the web, dark energy stretches it. We are living in the era of the cosmic tug of war. For billions of years, dark matter held the upper hand, and the universe slowed down its expansion, allowing the web to form. But about 5 or 6 billion years ago, the density of matter dropped enough due to expansion that dark energy took over. The expansion began to accelerate. The drift is now fighting a current that seeks to disperse it. This acceleration means that the cosmic web is freezing in place. The flow of matter from the voids into the filaments is slowing down as the voids expand faster than the matter can fall. the largest structures in the universe, the superclusters, are likely the last ones that will ever form. Gravity can no longer bridge the ever-widening gaps. We are witnessing the peak of cosmic structure. In the far future, the filaments will snap. The clusters will become isolated islands, and the sky will go dark as the other galaxies are carried away beyond the cosmic horizon. The drift of dark matter will eventually cease to build. It will only hold what it has already gathered. We are privileged to live in this golden age of structure, where the web is vibrant, connected, and visible, where we can trace the flow of the ghost and marvel at the architecture of the night. The search continues. New telescopes are being built, the Vera Rubin Observatory, which will map billions of galaxies, creating a movie of the universe that will reveal the shimmy and shake of the dark matter web over time. The Euclid mission, launching to space to measure the shapes of galaxies with unprecedented clarity. These instruments will turn the sky into a laboratory. They will test if dark matter is truly cold or if it has some warmth. They will test if it interacts with itself. They will map the detailed tomography of the dark universe. We are drawing a map of a land we cannot see, feeling the contours of the mountains with the tips of our fingers, guided by the light of the stars. The drift is slow, but our understanding is accelerating. We are learning to read the invisible, to hear the silence, and to appreciate the vast, dark scaffolding that holds us all